Again, you don't need to know the percentages. We're not even talking about how these percentages were determined. This math is way beyond the level that's required in this class. This is just an outcome. And it's one of the reasons why we really like talking about standard deviation as a measure of risk, because this kind of thing is true. It's been determined. Okay? And what's nice about this is that it's not just a math result, right? There are a lot of nice, pretty math results that don't seem to hold up in practice, but this isn't one of them. We see the bell curve in lots of natural phenomena, including stocks, right? So this is a graph, this is a plot graph, a histogram of the annual return for the entire stock market in every year from 1826 to 2013, sorry. So it's a few years out of date. I need to get this up to date. And what I did was look at the bins along the bottom row, right? The bins are percentage return for the stock market. So the farthest left bin is -50 to -40. That means the entire stock market lost half its value in that year. Then -40 to -30, -30 to -10. That center line, that's the tallest, that's 0 to 10%. The stock market made 0 to 10%. Then 10 to 20, all the way up to 50 to 60. I estimate the actual return of the stock market in that year. How much did the average stock market move? And then I put that year into the bin where it represents, right? Now notice that even though it's not like perfectly smooth, it has the same representative figure as the normal distribution bell curve. We think that this is the distribution more or less that guides the probability of making a return in the stock market. And you can see that the great majority of years are right in that center column, right? That's like 40 years of the last 200. There's been a return in the stock market between 0 and 10% positive amount, right? And the farther away we get from that expected return, and the expected return, by the way, in the stock market is 8 to 11%. So that's exactly where it should be, right? That line is right in the middle. The farther we get from the expected return, the smaller number of years are in there. And that's more or less in line with exactly how we think about risk, right? The risk of the most extreme outcomes is really small relative to the risk of less extreme outcomes, right? And here we would say the probability of some really extreme outcome occurring is much smaller than the probability of some outcome that is much closer to what we think is going to happen, right? So what we think is going to happen is the expected return. And notice that the majority of years are grouped here within, one bar of the expected return. So between -10% and +20%, we see the vast majority, about 68% of our outcomes fall into this range. This is our idea of +1 standard deviation, -1 standard deviation. Right? And then we see that, then a smaller percentage are in those medium ranges, the -30 to -10, and the +20 to +40. We still have a good number of years that fall into those return ranges, but a lot less. And then those really extreme ones, the -30 to -50, and the 40 to 60, +40 to +60, not very many years are either that bad or that good. And that's probably good for us, right? I mean, notice that like the worst year we ever had, 1931, the height of the Great Depression. And we can see all of the ones in yellow, all the years in yellow, that's the Great Depression and surrounding. So it starts in 1929, or actually I even put 28 in there. Look at 1928, it's over on the right-hand side and +40 to +50. Great year in 1928. 1929, the start of the Great Depression in September. Black Tuesday, stock market crashes, people throwing themselves out the window, stock market loses 10%. Right? Then 1930 loses another 10%. Then 1930 it loses 25%. 1931 it loses 50%. Within those 3 years, the stock market drops almost 80%. But then what happens? Look at 1932 and 1933 and 35. Some of the best years the market's ever had. Right? So we get a lot of swinging around. The swinging around, the bouncing back and forth, that's risk, right? In none of those years were we at the expected return. And then look at the ones in blue. That's the financial crisis. 2008, we lose 35%. But then in all the years after that, we just keep making more money. 2009, 25%. 2013, 30%. But from 2008 onwards, the stock market, until this latest crash, had gained almost 300%, right? So tripled your money. So there's a lot of variation here, and this idea of risk as a distribution, as a probability-weighted distribution, is played out in the data. I mean, that's what this graph shows. Pretty similar. It's not exactly the same, but the more years we put in here, if we had 1,000 years of stock market data, we would get a much smoother line. Okay. This data plays out in all kinds of other natural phenomena. We see it in height, right? So if you lined up people by height, you would find that the people that are extremely tall or extremely short, there aren't that many of them, but there's lots and lots of people that are right around the average height. Right? This was developed, actually, this kind of distribution was really developed when we thought about, when a professor was looking at grade distributions. That's where the bell curve idea comes from, and grading on a curve, that's what this is all about. And you see that grades fall into this distribution pretty naturally with enough students. That the majority of people are right around the average grade, 70, 80. Some people get really good grades, some people get really bad grades, but those people are less and less the farther out you go. So how do we actually estimate a measure of risk? Well, that is by a formula called the Variance Formula. And the variance is the weighted average of squared deviations from the expected return, which is a mouthful. But again, don't get intimidated by the formula. The formula is just a different language, and you just have to be able to translate the language. So this says the sigma squared, which is our term for the variance, is equal to the sum of the probability of each outcome times the difference between the actual outcome, that's R, and the expected outcome, that's the expected return, squared, right? So again, what we're interested in is how do all of the potential outcomes differ from what we expect? Because that's what risk is, okay? So we'll work a couple of examples here. We're gonna work a simple example with just 2 states. We'll work a more complex example with 3 states. So please go jump and see those examples right here. And of course, as always, the solutions are here in the slides. But I guess that's less important if you also have a video where we work the solutions out.